need some tools. Like this may be applied to some other problems also. We'll rigorously develop everything. Okay. The first one result about symmetric matrices. If you have if A and B are symmetric matrices, let A and B both are real symmetric matrices. Symmetric matrices, and B is positive semi-definite. B is PST. Then we can compare the eigenvalues of A and A plus B. Okay. In general, if you have two matrices A and B, we don't have any meaningful relation between sums and the individual eigenvalues of the individual matrices. Okay, so if A is symmetric and B is symmetric and positive semi-definite, then we have this relation: lambda I of A is less than or equal to lambda I of A plus B. This holds true for every I equal to 1 to n. Okay, so yeah. So I'm not going to give a proof of it. The proof is similar to the characterization, variational characterization, the proofs we have seen many times. Like we have to cleverly construct a vector which is sitting inside in intersection of two subspaces. Okay, just you can take this as an exercise. You read the proofs of the variational characterization for eigenvalues. Okay, so the same technique will work here. Okay, we try to prove it. So we will use this theorem to prove our results. So one immediate consequence of this result is, if I have a spanning subgraph of a graph G, okay, G be a graph and H be a subgraph. Okay, so if H is just a subgraph, then we don't know any relation between or we don't have interlacing sort of thing between the Laplacian matrices, the Laplacian eigenvalues of G and Laplacian eigenvalues of H. If it is spanning subgraph, okay, then we have a relation. We can just apply this theorem there. Okay, so then the ith eigenvalue of the subgraph H should be less than or equal to the ith eigenvalue of the graph G. This holds true for all I equal to 1 to n. Okay, for arbitrary subgraphs we don't have any interlacing type of things. Okay, if it is a spanning subgraph, then we do have this result. Okay. So how to show that? The proof is simple.
Or eigenvalues of the adjacency or
Laplacian. So, today whole day I am talking about only Laplacian. Okay, so lambda 1 less than or equal to lambda 2 eigenvalues of L of G. Yes.
Why they tell me, why you say that it's not for the
if it is just a subgraph, the Laplacian corresponding to the subgraph need not be the principal submatrix of the Laplacian of the supergraph. Degrees may vary, right? The subgraph degree will differ, the supergraph degrees may different. If it is a spanning subgraph, you will see. It need not be a submatrix, but it will differ by a positive semi-definite matrix. Yeah, we will discuss that. Okay, so let us see what. First, we will prove it, and then we will come to that point. So let us take H be a spanning. H is a spanning subgraph. H1 let us define be a spanning subgraph. Spanning subgraph of G such that, so it's a spanning subgraph, so vertex set of H1 is vertex set of G, the edge set of H1 is, you take the edge set of G and then just remove the edges of H. Okay. Then what about Laplacian? L of Hn equal to, or L of G equal to L of H1, L of H plus L of H1. Okay. So H1 is a subgraph. So H1 is positive semi-definite. Hence you have this relation. Okay. So by the previous theorem, we have lambda I of G is less than or equal to lambda I of lambda I of H is less than or equal to lambda I of G for all I equal to 1 to n. Okay, so what is your question?
It's not for any subgraph. So I to say that if it is any subgraph, then it can.
Yeah, that you can append zeros and then you can apply this result for that. Okay, the interlacing result, whatever Sebi was proving in the morning. So that there you need a principal submatrix. So in general, when you take the Laplacian of a subgraph, the Laplacian need not be a principal submatrix of the Laplacian of the original graph. Okay. So in that aspect, suppose if you see, you give me, so that's also induced subgraphs, not any subgraph. Okay.
So here spanning subgraph, it could contain isolated vertices.
Yes. And here this is also, this need not be induced also. Okay, when you are doing isolated vertices and all. Yeah, then for any subgraph you can apply this with isolated vertices. Then for Laplacian, in a sense, it's much stronger than what we had for adjacency case. Right. Yeah, good. So let us use this result to show the Laplacian eigenvalue of any graph is less than or equal to n. Okay, that's kind of trivial. Why it's the case? Yeah, complete graph has the largest eigenvalue of lambda n of kn is equal to n. Therefore, lambda n of any graph G on n vertices should be less than or equal to n, because kn can be written as, you take G plus G complement, then you can write down or G, the decomposition whatever we did. Okay, G and the G1 you define, so it will cover the entire kn. This is less than or equal to n. Okay. Now the main result is when the largest eigenvalue, largest Laplacian eigenvalue is equal to n. Okay, so let's prove that. We need the concept of join. The join of two graphs G and H, this is denoted by is obtained by adding all possible edges from G to H. Okay, from every vertex of G, draw edge to every vertex of G to every vertex of H, draw all possible edges. Okay, is obtained by adding edges between G and H such that every vertex in G is adjacent to every vertex in H. Okay, so let us see an example. So you take G to be something like this and H to be some triangle. Then what is join of G and H? Just a small example, okay. Something like this. Okay. The result says that so the main result which I am going to discuss says that the largest eigenvalue of a graph G is equal to n if and only if the graph G is a join of two graphs. Okay, that's what we are going to prove. So before that, if G and H are graphs, if you know all the Laplacian eigenvalues of G and H, then we can derive or we can get a formula for all the Laplacian eigenvalues of G join H. Okay, so that I will prove the formula first. So let us take G1 and G2 be graphs on n1 and n2 vertices, okay, respectively. So if the eigenvalues of G1 are the eigenvalues of G1, okay, of L of G1, let's say these are all 0 which is equal to lambda 1 less than or equal to lambda 2 less than or equal to lambda n1, and the eigenvalues of L of G1, G2 are 0 which is equal to mu1 less than or equal to mu2 less than or equal to mu n2. If you have the complete information about the eigenvalues of the individual graph, then the eigenvalues of the join, the eigenvalues of the Laplacian matrix of the join is given by, so 0 should be there irrespective of whatever graph you are taking. 0 is part of the spectrum always, and then n2 plus lambda 2, n2 plus lambda 3, n2 plus lambda n, n1 plus mu 2, n1 plus mu 3, n1 plus mu n, and then n1 plus n2. Okay, so we have n1 plus n2 eigenvalues. Everything is covered here. Proof. 0 is an eigenvalue because you take all one's vector, that is done. For the rest of them we have to see. Okay, just you have to cleverly like give the labeling for the vertices. Okay, so let us choose the labeling for the vertices in this way. Okay, the way is first keep all the vertices of G1 first, okay, and then keep all the vertices of G2. Okay, so in this notation, can we fill this? Laplacian of G, this is equal to Laplacian of G1 plus how many vertices, how many edges we added? N2. So from here to, so this side we have N2, this side we have N1. So in this part we are adding N2 edges. So N2 times identity. Then minus J. Okay. because between any two vertices of G1 and G2 you have edge. Okay, and symmetrically fill here, this is minus j, and this part L of G2 plus N1 times identity. Okay, with this proper labeling we are getting in the nice format. Okay, so now let us look into so this is again a nice guess. You take the vector y to be equal to n2 times in1 minus n1 times in2. Okay, so block vector n2 times in1, not in1, I want to see en1 or 1n1, using this notation for, it is a column vector whose all entries are equal to 1 of size n1. Okay, so this is the column vector of size n2 with all ones. Okay, so this is basically first n1 places I am keeping n2, the remaining places we are keeping minus n1. Okay, so for this vector let us see what's happening. So LG of y minus L of G1 plus n2 times identity minus j L of G2 plus n1 times identity. So we are going to do the block multiplication. This is n2 times all ones of size n1 minus n1 times all ones of size n2. Do the multiplication, what are you getting? L of G1 into n2 1n, that is 0, because row sum of L of G1 is 0, hence the first part vanishes. What about the second part? We are getting n square into n square into, we are multiplying with the identity, so it will stay as it is. Sorry, n2 square into all ones vector of size n1, then what you will get? n1 into n2. So this is plus n1 into n2 into all ones vectors of size n2. What about the next row? n1 plus n2, yes, n1 plus n2. Okay, yeah. Here number of rows is n1, so this is n1 by n2. Okay, yeah, you're right. Correct. So this is n1. Yeah, right. Otherwise, sum is not compactable. Yeah. So what about the next term? This is minus n2 into n1 1n2 minus n1 square into 1n2. So let us take an n2 common from the first term. So this is n2 into n1 plus n1, n1 plus n2 into n1 plus n2 into 1n1. From here let us take n1 common out. Are we done? It is nothing but negative of, not negative, this is same as n1 plus n2 into n2 1n1 n2. That's the eigen equation. Okay, so we have seen 0 is an eigenvalue and n1 plus n2 is an eigenvalue. Okay, so far we didn't use any of the eigen equations corresponding to L of G1 and L of G2. If you use that, we will get rest of them. Okay, the crucial fact is If you take any eigenvector corresponding to the non-zero eigenvalues starting from lambda 2, they are all perpendicular to all ones vector. J has all ones. If you multiply J with that eigenvectors, you are going to get 0. Okay, so let us do that. So if so this is one part. So if we take xi is an eigenvector of L1 corresponding to the eigenvalue lambda corresponding to lambda I. Okay, let's say for 2 less than or equal to I less than or equal to n, then you define yi equal to xi and zeros. You add n2 number of zeros with it. Okay, so xi is the eigenvector of L1 corresponding to the eigenvalue lambda I. Now from that xi we are constructing a vector yi, okay, by appending just n2 zeros. Okay, so now let us see this, whether it satisfies the eigen equation or not. Minus I minus j L of G2 plus n1 times identity. This is xi 0. What do you get? So first entry LG1 xi, that is just lambda I, n2i, that is n2. Okay, so this is same as n2 plus lambda I xi. Second entry is j multiplied with xi. Xi is the eigenvector corresponding to non-zero or second corresponding to the rest of the eigenvalues other than lambda 1. Hence is orthogonal to all ones vector. So this will give me 0. Xi is different from 0. Hence this is an eigenvector corresponding to the eigenvalue n2 plus lambda 1, lambda i's. Okay. Then you can guess what are the rest of the eigenvalues by guessing the eigenvectors. Swap the role of, like, replace the role of xi by yi's. So here 0 and then keep yi's here. If you take yi's to be not yi's, maybe some zi's you take. Zi's to be the eigenvectors of this matrix L of G2 corresponding to the eigenvalues mu2 to mu n2. Then you are going to get rest of them. Okay, this gives a complete description of all the eigen. Okay, so whenever performing operations on two different graphs, it's always good to identify a proper labeling. Okay, if you can identify a proper labeling corresponding to the labeling, if the matrix has some nice structure, it will be easy to handle. Okay, for joins, like this is useful. This one. Yes, Sabi. So the students argued that if I take any subgraph, which is if not even a spanning subgraph, then I can append isolated vertices and the still results holds true. Yes. That means that this interlacing holds true for one side of the interlacing holds true for any subgraph for Laplacian.
Yes, I mean, yeah, something like that. But it's special for the Laplacian. You don't get anything.
Yeah, for the adjacency matrix. Yeah. And again, the other side you can't argue, right? Only the half of the interlacing holds true. Yeah, that's true. Up to that part is fine. Yeah. Good. Okay, good.
You're saying if and only.
No, I'm saying only one side. If and only if I don't know. What about the converse? What do you define converse? It's only one side I'm stating. Okay. Okay, so let us state the main result. Theorem. Let G be a graph on n vertices. Then let G be a graph on n vertices. Then n is an eigenvalue of the Laplacian L of G if and only if G is join of two graphs. G is the join of two graphs. Okay. So one side of the result is already proved. Can you say which direction we proved already? If G is join of two graphs, then n is an eigenvalue. That follows from here directly. Okay. So proof: if n is a if G is a join of two graphs, then n is an eigenvalue of the Laplacian of G. Okay, that follows from here. That theorem, okay, the theorem which we proved. Okay, so to prove the other direction, let us take G is not a suppose that, okay, maybe let us assume n is an eigenvalue of G, n is an eigenvalue of L of G. Okay, suppose that G is not a join of two graphs. G is not a join of two graphs. So now consider this non-negative matrix L plus J. Okay, this is a non-negative matrix. Right, the Laplacian only the negative entries were in the off diagonal. Now we have added this J, so everything is non-negative now. Also note that this L plus J into E. E stands for the all ones vector. Can you evaluate this?
Diagonal of every entry is
LE equal to 0. LE all ones vector. Okay, this is just n times E. So n is an eigenvalue of this matrix. Okay, so n is an eigenvalue of L plus J. Okay. So since G is not a join of two graphs, okay, so we cannot write this L plus J as the following form. Okay, we cannot write L plus J the block form something like this. Okay. Oops. Or L cannot be written in this way. Okay. That means that if you consider this matrix L plus J, this is irreducible. So irreducible, like if you don't know what is irreducible, just draw a graph associated with this matrix L plus J, okay, as follows. The vertices of just the rows of this matrix or columns of this matrix, and you are going to keep an edge between two vertices I and J only when the corresponding entry is different from 0. Okay, so we have seen this notion for 0, 1 matrices, okay, that can be extended for arbitrary non-negative matrices. Okay, so L plus J, this is a matrix of size n. You draw a graph of size graph with n vertices. Okay, so you keep an edge between the vertices I and J only when this L plus J ijth entry is different from 0. Okay, so and the Perron-Frobenius, whatever we discussed for 0, 1 adjacency matrices, okay, that holds true for arbitrary irreducible non-negative matrices. That says that the largest eigenvalue of L plus J is simple. Okay. Can you complete the proof? So by Perron-Frobenius, the largest eigenvalue of L plus J is simple. And what are the eigenvalues of L plus J? The eigenvalues of L plus J are so lambda 2 to lambda n, and then n. We know lambda n is less than or equal to n for everything. Okay, that means that n has multiplicity equal to 1, so lambda n should be strictly less than n. Okay, so that is lambda n strictly less than n, but we started with the assumption that n is an eigenvalue of L of G. Okay, so lambda 2 to lambda n are the possible non-zero eigenvalues. Okay, when the largest eigenvalue is strictly less than n, hence the eigenvalue n cannot be an eigenvalue for L of G. Okay, so this completes the proof of fact that n is an eigenvalue of the Laplacian if and only if it is join of two graphs.
If G is not a joint, then we cannot write L equal to this. So where are we getting this?
If you can't write down in this way, then when you are adding J to it, if you can write in this way, what is the meaning? L plus J will be L1 0 0 L2 2. So that is reducible. If you cannot write down in this form, then it is irreducible. Okay.
So why are the eigenvalues of L plus J lambda 2?
Oh, you can calculate it. So J advantage is like if you hit with any of the eigenvector other than the eigenvector corresponding to 0, everything it will vanish. So L plus J of, you take any eigenvalue u orthogonal to eigenvector, it's the same as Lu, it's the same as lambda I into u. So u2 to un it will be preserved. Lambda 2 to lambda n with the same eigenvector. Okay. The only left out thing is that n. I will do that, maybe after that we will try to connect it. Okay. Yeah. So in adjacency matrices, like if you know the spectrum of the graph, then you can't say much about the spectrum of its complement. Okay, but in the Laplacian case we can say something. Okay, that say everything. Let us see what. So if lambda is an eigenvalue of let's say L of G, okay. Okay, so maybe let us observe something first. So what is L of G plus L of G complement? This is same as n minus 1 identity minus j yeah, this is the one, right? Okay. One is captured here also. Ni minus j. So L of g is equal to n minus j minus L of g complement. So if lambda is an eigenvalue of L of g, let us take this different from 0, then if L of this, let's say lambda u, so this implies n I minus j minus L of g complement times u, this is equal to Lg of u, which is equal to lambda u. So this is just nu minus, so I have taken the eigenvalue other than 0 or starting from the second smallest eigenvalue. So ju is 0, so here this is just L of g complement to u, this is equal to lambda u. Okay, so L of g complement of u, this is equal to n minus lambda into. So if the spectrum of L of g is the spectrum of L of g is 0 lambda 2 to lambda n, then what is the spectrum of L of g complement? 0 n minus lambda 2 n minus lambda n. Okay, so if you know the Laplacian spectrum of a graph, then you know the complement of it. Okay, so SEBI suggested a problem. You can calculate the eigenvalues of complete bipartite graph using.
I mean, for this one, you can also using this thing. So I think if you have n is an eigenvalue of Lg, by this, like if n is an eigenvalue of Lg, so your lambda n is going to be n or something, one of those. Then the spectrum of the complement of G will contain two zeros. And because it contains two zeros, the graph is going to be disconnected. And so the complement of it is going to be disconnected. And if the complement is disconnected, then G itself is going to be a joint of those
two parts.
Yeah. So that's kind of
that gives another proof for that.
So this is an easy tool if you want to calculate. If you have graphs and you don't know how to calculate, you can think about this. Replace your graph by the complement and see if the complement is easy to calculate. Then you can play with this game. Like for example, like complete bipartite. Like you can give them the complete bipartite graph. Maybe you don't know, but if you take the complement of the complete bipartite, you have two disjoint cliques. So you have the eigenvalues, and then you get the complement very easy. It's just a nice trick.
Yeah. Okay. Okay, so maybe I will just state the statement of matrix Forest theorem. I think some of you are asking. For general subset itself, okay, I will state the matrix Forest theorem. From there you can see. I am not going to prove, as I said. So this says that so let G be a graph and vertex set of G is equal to 1 to n. You take any subset, okay, any proper subset, non-empty proper subset of the vertices, okay. Now you look at the determinant of so this notation, this open bracket W by W stands for you remove the rows and columns corresponding to the indices of W, okay, from the Laplacian matrix. You take the Laplacian matrix, from the Laplacian matrix, remove the rows and columns corresponding to the index set W. The matrix tree theorem, we took W to be a singleton set, okay, removed one row and one column. So here we are removing this. Okay, so this quantity, this is equal to, okay, the number of spanning forest with the cardinality of W components okay. If you take W to be singleton, you have a forest with only one component, okay. So here you have a forest with the cardinality of W, spanning forest with the cardinality of W components. So with one more thing, every component of the spanning forest contains exactly one vertex of W, okay. So every component contains one vertex of W, okay. This is the general matrix forest theorem. Okay, so maybe one more interesting consequence of matrix tree theorem, whatever proof Sebi gave. So you can give a spectral formula for the number of spanning tree. So morning we saw the formula. What was the formula? Determinant of, so matrix tree theorem says that this tau of G, the number of spanning trees is equal to determinant of, sorry, determinant of, you take LIA. Okay, so this quantity indeed this is same as you take all the eigenvalues starting from 2 to n, okay, 2 to n, just take the product of them, divide by n, you will get the number of spanning trees. It's a proper spectral formula, you can say, okay. So how to prove, any idea? Sorry? Yes, coefficient of x in the characteristic polynomial. Okay, so if you remember in the first lecture I said something about the coefficients of the characteristic polynomial. They are nothing but sum of the principal minors of order n minus 1 by n minus 1. Okay. So how many principal minors we have? N principal minors, okay. And the other way to look at the same coefficient is sum of the products of the eigenvalues taken n minus 1 at a time, okay. So lambda 1 equal to 0 for every graph, okay. So if you have to avoid lambda 1, then we have only one product, that is lambda 2 to lambda n. So lambda 2 to lambda n is equal to n times the number of spanning trees. So hence the number of spanning trees is equal to the product divided by n. Okay, good. You want to add anything? Laplacian, I'm not good at it. Anything we missed? Okay, then we'll stop here. Okay, can stop.